Okay, before we start looking at how to differentiate the natural log function, let's have a reminder of what a log function is all about. Really, it's about asking a question, like, if it's log base 2, 2 to the power of what equals x? Well, for instance, 2 to the power of 1 equals 2. 2 to the power of what equals 4? Well, it's 2, and that's the y value. 2 to the power of 3 equals 8, and 2 to the power of 4 equals 16. So if we just change this and we take the log base 10, then we're asking the same thing, but it's 10 to the power of what equals x. Because of this, 10 to the power of 2 will take us right off the graph. What if we change this to be base e, e being Euler's number? Then we've got the function that looks like this, and if I want to say e to the power of what equals 1, well, it's 2.718. We can see that natural log and log base e are actually the same thing, two names for the same function. Looking at the gradient, you can see that the gradient of this function never gets to infinity, and it also never gets to 0. So it's always positive. It's always decreasing as you go to the right, but never quite gets to 0. And if we go backwards, when x is equal to 0, it's undefined. So how do we differentiate this? Well, we first need to realize that the gradient of our function, log of x, natural log of x, is inversely proportionate to x. That means as x gets bigger, the gradient gets smaller. So the derivative of natural log of x is just going to be 1 over x, showing this inverse proportional relationship. So natural log of x differentiates to 1 over x. What about natural log of 2x? Well, we have to use the chain rule, so the inner function will be 2x, which will derive to 2. Now applying the chain rule, we've got 1 over g times g prime, giving us 2 over 2x, which equals 1 over x. So it's actually the same answer. Right, let's try a trickier example now. Natural log of e to the x. So we have to use the chain rule again, and we'll call our inner function g e to the x, which from the previous video we know differentiates to e to the x. We'll call our outer function f, that's natural log of g, therefore it differentiates to 1 over g, and applying our chain rule, which by the way is df dg times dg dx, not df dx, we get 1 over g times e to the x, which is 1 over e to the x times e to the x. This all simplifies down to 1. Looking at our graphs, of course, we can also do this another way and say, well, the exponential graph is the inverse graph of natural log. So in fact they cancel each other out, and we've just got the function y equals x, which we could have just used at the start.